Hello! Welcome to A9AYTZ2XZR, the best among the best. My name is Julie and I will be your instructor as we read through high-grade potash from low-grade ore. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at A9AYTZ2XZR. The link is in the description. The objective of this report is to give detailed information on the production of high-grade potash from low-grade ore. A group research project was carried out to find the different aspects there are to know as processing engineers in the potash industry or related fields. It discusses the background, raw materials and uses of potash. Further detail is given on the different process routes followed to get high-grade potash. It was found that there are three main process routes used to extract potash from brine include flotation, thermal dissolution and thermal crystallization. Another option is the ammoniacal leaching process. However, it was concluded that the best one is flotation as it is cost-effective. Raw materials used in potash production include water, HCl and polyethylene glycol. Unit operations for obtaining potash were found to be dewatering and drying, separation and product screening performed respectively. Uses of potash are mainly industrial and agricultural. Mining potash can be hazardous to people, the surrounding and machinery, hence safety must be practiced on site. Ultimately, information gathered on economics show that it is important to consider cost and how to effectively minimize it during the planning stage of a potash mine process plant development. 200 words. The objective of this report is to give detailed information on the production of high-grade potash from low-grade ore, of teamwork and also the challenges of working as a group. Potash is a term generally used to define all derivatives of potassium. The term potash is derived from the old method of producing potassium carbonate by leaching wood ashes and evaporating the solutions in large iron pots. The white residue left in the pot was called potash. Can, 1976. The original use of potash was in agriculture and with time, more were discovered. As a fertilizer, it is usually added to soil to compensate for chemical deficiencies. It contributes to healthy plant growth and promotes development of root systems. Potassium is a primary macronutrient and is needed in very large amounts by plants. The commonly used form of fertilizer is potassium chloride or muriate of potash. The main use of potash is that it is used as a fertilizer to stimulate the growth and increase the yield of crop plants, providing synthesis of starches and sugars. Other uses of potash are mainly industrial production, for example manufacture of pharmaceuticals and insecticides. Andrews, 1991. Potash occurs as a widespread thick accumulation of marine chloride deposits. This is accumulation of salt minerals deposited in structural sedimentary basins through the evaporation of seawater. Surface geophysical techniques that have been used for many years that prove to be most economical are gravity and seismic methods. This is because they are very useful in determining the distribution and shape of evaporate bodies. Andrews, 1991. Due to its high demand, potash is now largely mined, especially in Canadian mines like Saskatchewan. These mines produce soluble potassium salts present in crystalline forms in salt deposits. Can, 1976. More of this is also extracted from concentrated brine surfaces in different lakes around the world. This report focuses more on the underground extraction of potash using brine. Furthermore, it explains different processes used to produce potash from low-grade ore. Potash ore consists of sylvite, KCl, carnallite and halite. The preferred process was chosen to be flotation, amongst others to be mentioned later in this report due to its cost-effective processes. Potash is graded according to its potassium oxide content. Garrett, 1996. This report covers 6 main subjects of concern in the design process of a potash plant. The team engaged in the process route evaluation, process selection and preparing process flow diagrams, section 3.5. This section is based on feasibility studies of the product. It focuses on identifying all the process routes and all the process chemistry involved in them. The best route was selected looking at different factors. These include thermodynamics of reactions, physical properties of chemicals used in the production of potash. It also covers the unit operations required to carry out the process, chemicals required and their sources, but most importantly the economic viability and safety were considered in choosing the process route flotation. This section also includes process flow diagrams of the different identified processes. These were prepared using the Proceed software. Mang Charles covered the section on the sources and properties of raw material feedstock, 3.6 in relation to the selected process. This part examines reagents, reactants, catalysts and absorbents used in the production of potash, including their sources and suppliers. It discusses the chemicals used and their properties in relation to the process route chosen. A cost forecast is also provided, mentioning also the contributing factors to availability of the raw materials. Section 3.7 on unit operations and assessment of material of construction was done by Aubrey Ramikoba. It clarifies in detail the unit operations that occur in potash processing. Potential problems of potash processing are also analyzed in this section. Process chemistry, process operations and associated challenges. This subtopic was covered by Marco Mazzani. It includes explanations and discussions of thermodynamics and kinetics of the main reaction chosen in production and processing of potash. Utzel wrote on the uses and applications of both processed and raw potash, 3.9. Further examination of the possible markets of potassium derivatives was examined, covering both current and future market demands of potash. Political effects on prices are also clarified, including how competitors affect the potash market. Part 3.10 on safety, health and environmental issues was covered by Waturo K. Rana. This section discusses intrinsic hazards in the processing of potash. Risks posed by both material/equipment and workmen on site were covered. Suggestions were made as to how these can be avoided. It relates the chosen process to its potential environmental impacts, including transporting and generating potash. 3.11. This section on process economics was covered by Giulio da Costa. It reflects on all figures/number working involved in processing potash. Cost of production, running and maintenance of a potash plant were covered, as well as external factors that could influence this. 842. Potash processing is one of the most running processes in the present world. Due to its high degree of applied uses and varying reserves, a number of beneficiation processes have been formulated to try to extract it from its ores as efficient as possible. Some of these processes include flotation, heavy media separation, electrostatic separation, and last but not least, thermal dissolution and crystallization. Even though they are often mixed, the most currently employed processes are flotation and thermal dissolution and crystallization. Flotation is basically a standard method formulated for separating potash from its accompanying halide. This is a selective beneficiation process which utilizes differences in surface properties of various minerals. By conditioning ores with others such as methyl isobutylcarbonyl, selected minerals can be driven to become either hydrophobic, water repellent, or hydrophilic, water attracting. A treated solution is then agitated to allow even distribution of reactants and blown with high-velocity air, normally from the bottom of the reactor, to form bubbles in which potash mineral are collected in before they coalesce as they rise to the solution surface for collection, whereas the gangue all settles at the bottom of the reactor as it is rendered hydrophilic. As mentioned earlier on, thermal dissolution and crystallization is also employed in this process, is primarily based on the fact that potassium chloride is much more soluble in hot water than in cold one, whereas sodium chloride, halide, is on slightly more soluble at 1000 C than it is at 200 C. In a saturated solution of both salts, sodium chloride proves to be less soluble at higher temperatures. Knowing this, after the ore has undergone all necessary comminution routes, it is washed with cold but saturated brine solution before desliming, and the resultant solution is then heated to dissolve potash before filtration. The potash solution is then cooled slowly to crystallize it, and the purity is normally found to be a stunning 99.9% at most. Despite the efficiency of the above process, flotation is widely used as it allows much more potash production in a single shot, thus making it more economical. Potash is mainly used as a fertilizer and in industrial processing. Most of potash, about 95%, is used for fertilizers. Potash 1, 2010. Potash fertilization started in the 19th century when Justus V. Liebig discovered that plants need, in different parts and quantities, nutrients such as nitrogen, phosphorus and potassium, in order to build up biomass. Today, potassium deficiency is recognized as an important limiting reason in crop production, MON, 2001, and the main symptoms of potash deficiency include low strength of plant, less resistance to low water availability and less resistance to fungus diseases. Potash is needed by plants to prevent unnecessary water loss by transpiration. It is essential for the development of the root system and fosters nitrogen fixation of leguminous crops and increases plant resistance to drought, frost and to a number of diseases and pests. Potassium improves the size and color of crops such as fruits and enhances their quality through an increase in sugar content of crops such as fruits, carrots, onions, and sweet potatoes. Hence it is used widely in commercial farming to increase crop yields. In industry, potassium carbonate has been used for soap, glass, and china production. In the laboratory, it may be used as a mild drying agent where other drying agents such as calcium chloride may be incompatible. Potassium hydroxide used in the manufacture of biodiesel, manufacture of soaps and as an electrolyte. Potassium chloride is used for the manufacture of potassium metal, medicine, food processing and as a substitute for table salt. SOPIB, 2001. Potassium is largely used in rocket propellants, toothpaste, fireworks and for food preservation, for example in meat. SOPIB, 2001, water, H2O, most common compound on Earth which can exist as both solid, ice, liquid, water, and gas, vapor. It is a chemical compound of hydrogen and oxygen with a relative molecular mass of 18. Pure water is colorless, odorless and tasteless with a freezing point at 0 and a boiling point of 100. Water is a good solvent due to the attraction between the negatively charged oxygen atoms and positively charged hydrogen atoms. It also has a high heat capacity, therefore requires large amounts of energy to raise temperatures. Water is incompressible and produces high surface tension due to the atomic attraction force. Guarantee gums yellowish tasteless and odorless carbohydrate with excellent water solubility because of the strong hydrogen bonds but insoluble in alcohol. It hydrates rapidly in cold water to give a highly viscous pseudo-solution of low shear viscosity compared to other hydrocolloids. Very thick sapropic at high concentrations, 1% and is a better emulsifier as it has more galactose branch points. It is non-ionic there it is not affected by ionic strength or pH and it does not form gels but displays good stability to freeze-thaw cycles. Taloamines made from tallows and used as chemical fertilizer anti-caking and or floating agent, stabilizer, amines act as nucleophiles. At ambient temperatures it appears as an odorless white semi-solid substance. It is not an oxidizing agent therefore is not reactive with low solubility in common solvents. It has a negative shock, thermal and friction sensitivity therefore non-explosive however can form an explosive dust-air mixture. Its melting point ranges between 56 to 92 and a boiling point of equals 280. Hydrochloric acid it is a clear colorless solution which is concentration dependent. It has an odor of a pungent hydrochloric acid with infinite solubility. Its vapor pressure and evaporation rate is equivalent to that of water. When heated to decomposition, it emits toxic HCl fumes and explosive hydrogen fumes. Exposure to direct heat and sunshine should therefore be avoided. Very corrosive as liquid and mist can cause severe body harm. Polyethylene glycol used as a thickener in many products due to its stability. It is a clear to white semi-solid polymer with a melting point of up to 67. It is non-toxic, odorless, neutral, lubricating non-volatile and non-irritating but can be harmful if ingested or absorbed through the skin. It is soluble in water and many other organic solvents. Methyl isobutylcarbinol it is classified as a primary alcohol, methanol, and used as a solvent to promote froth, flotation agent. It is a clear, flammable and slightly soluble liquid with a melting point of -90 and boiling point of 131. It is a partially soluble in water but very soluble in alcohols, ether and most organic solvents. It is stable under ordinary conditions but reacts with strong oxidants. This part discusses the thermodynamic properties and reactions of potassium chloride, PCl5. These will include the density, viscosity and heats of reactions involved in the production of potash. As expected with most materials, the density of potassium chloride is directly proportional to the increment of the concentration, Garrett, 1996, which has been proven experimentally by a lot of researchers. A sample plot is shown below. The plot illustrates how density of the material varies with concentration and temperature. It states that the density of PCl5 ranges from 0.92 at high temperatures, about 150, with low concentrations, and the highest density occurs at room temperature with a significantly high concentration. Figure 3.5.4.1 Density of PCl5 as it varies with concentration and temperature. Read above equation can also be altered by adding and replacing some of the terms to deduce a relation to calculate the heat capacity and specific heat of solutions involved in the processing of potash. Reactions of producing potash are mostly exothermic, although there are a few that are endothermic. Garrett, 1996. Other solutions that may be used in the steps leading to the obtaining of potash are listed below. Some of these could come about as side products that result from certain process routes. These are potassium carbonate, hydroxide, nitrate and sulfates of potassium. Garrett, 1996. Unit operations required to carry out the process mainly depend on the type of the ore used as the raw material. To obtain high-grade potash from a low-grade ore means that the unit operations employed should have a high efficiency, and also the quality of extracting the potash should be relatively high. Since most of the potash ores are found deep underground, about 2000 m, the most effective way of extracting raw potash is by using solution mining. It is then that potash goes through a series of unit operation to make it a high-grade product. Dewatering and drying. This is the first unit operation in the processing of potash. Dewatering is done by evaporating the liquid part that was used to extract potash from underground. The equipment used to evaporate the liquid part are the evaporators. Also, solar energy can be used to evaporate the halite from the potash. Most mines use the solar evaporation technique because it is cheap. After evaporation, heat is applied to potash. This is done by blowing a hot gas through the potash. As the gas passes through the potash, it evaporates the moist left, hence drying the potash. Roberts, 2009. Separation. The next unit operation is separating the pure potash from the waste, which is done mainly flotation. This is a physical separation technique which takes advantages of the different surface properties of various minerals. Garrett, 1996. In flotation, certain reagents are used called collectors. These are added to the potash. They would then absorb to pure potash only and make it waterphobic. MNT. When air is blown into the water with potash, the pure particles of potash will be attached to the air bubbles, hence it would float. To increase efficiency of flotation, many cells can be used. The figure below shows a typical flotation cell. Layton, 2005. Product screening. The screening of potash is the last stage or unit operation. Hydrocyclones are used to screen the pure potash from any other byproducts. MPT. They use the specific gravity of potash, which is different from other compounds found with it. Roberts, 2009. Rotex screens are used, which are efficient, and most of the product is retained. The quality of raw materials makes a difference in determining the end product. Therefore, it is very vital to ensure long-term, close and intensive relations between manufacturers and suppliers of raw materials. The raw water required for the project is assumed to be sourced from the nearby lake as determined by the site selection during the pre-feasibility study of the project. Water is one of the most important components that is required through the entire process down to the end product. In the solution mining, it is heated and pumped into the ore via the wells drilled on the ground. The fresh water is added to the already highly carnallite ores in order to dissolve magnesium chloride. Mostly the potash or liberated insoluble minerals are released by scrubbing the ore with saturated brine after crushing. The other uses of water at primary stages will be required during the crushing process and the impact crusher as a dust suppressor, thus making it a cleaner process compared to the dry crushing, which tends to be disadvantaged by difficulties as the dust collects despite being the simplest method for adoption. Measures should be taken to ensure that the natural resource is utilized sustainably by ensuring that the plant design incorporates water and brine recycling and the reuse or recycling drains and other bleed streams in order to capture and use the rainwater, thus minimizing freshwater usage. Freshwater is a stable, non-hazardous compound which can be incompatible with reactive metals. The water that is used in the processing of potash is obtained from the portable water supply and is therefore in abundance. Part of the plant water supply is tapped from the local municipal water reticulation network as a backup plan in the case of the breakdown of water treatment plant. The water should neither be acidic nor highly alkaline, as these conditions can cause unwarranted reactions with other reactants that are used in the recovery of potash. Water is the mostly used additive in the process from primary to the secondary stages. Talloamines. Tallow-based amines are hydrogenated hard fat of glyceryl esters of oleic, palmitic and stearic acids comprising of 16 to 18 carbon chains. Tallow-based amines are normally extracted from animal fatty deposits, especially from the fatty tissues of cattle and sheep. These tallow-based alkali amines are normally used in the synthesis of organic chemicals and cationic and amphoteric. Talloamines in this process are used as a collector. It is a cationic reagent which is attached by strong adsorption bonding. The long hydrocarbon chains of the amines are hydrophobic, which attaches to air bubbles in the flotation froth. Hydrochloric acid. The acids are used in the neutralization of the talloamines' alkalinity. These acids are in abundance from local suppliers and can be produced in-house by using the byproducts like sodium chloride tails. Hydrochloric acid is the solution of hydrogen chloride in water with a very high corrosive, strong mineral acid and can be found naturally in gastric acid. The byproduct, when common salts are converted to potash in the form of hydrogen chloride, is reacted to absorbed water gas in water. The reaction of sulfuric acid with potassium chloride to produce potassium sulfate and hydrochloric acid is an old process and is still employed to manufacture limited amounts of these products. The operation can however be competitive with other processes if there is a good sales market for the excess hydrochloric acid. If not, then the only feasible mode will be to outsource the chemical from the local chemical firms. Sourcing locally is regarded as cheap since the shipment of such chemicals can be cost-effectively negotiated. Table 1 highlight on the approximate regional prices of hydrochloric acid, including the price range that was observed over a period of 12 months. Guarantee beans gums. Guarantee beans are used as reagents which act as slimes depressants, due to their high galactose to mannose ratio. The guarantee plant Cymopsis tetragonalibus is an extremely drought-resistant plant which thrives in semi-arid regions, sandy soils, as too much precipitation make the plant too leafy, thus reducing the number of pods, which would in turn negatively affect the size and yield of seeds. These properties therefore make the guarantee very soluble in cold water, thus its suitability for various industrial applications. India has been and still is the major player in the production of the guarantee with a contribution of at least 80% of the global production. India exports 117,000 tons of guarantee gum and its derivatives comprising 33,000 tons of refined split guarantee and 84,000 of pulverized guarantee powder. Other than India, there are other players in the exportation of the guarantee like Pakistan, United States of America, Italy, Morocco, Spain, France, Greece and Germany. The guarantee market is influenced amongst other factors like the changes in production due to the fluctuations of rainfalls, demand and supply mismatch, hoarding/black marketing and governmental policies instituted by host producers. Despite the negative factors influencing the markets, its availability is reliably in abundance and can meet the demand and supply of the global market at the current trend. India is regarded as a stable country with regard to the risk and the political instability as per the World Competitiveness Yearbook, 2009, and also boasts of one of the major growing economies. 3-methyl isobutylcarbinol is primarily a short-chain alcohol which is widely used as solvent, fuel and chemical raw material. It is a hydroxyl group compound which is polar, therefore very soluble in water. Alcohols are very weak acids as they lose hydrogen cations, thus undergoes dehydration reaction, which mean eliminating water molecules. Natural gas is mostly and economically used in the production of the alcohol, but other feedstock is used to produce by steam reforming. Coal, due to its abundance, is also widely used as a feedstock, especially in China. Biomass gasification can also be used in the production of the methyl isobutylcarbonyl. Natural gas. Natural gas is regarded as the cleanest fuel of the 21st century so far, and it is regarded as the fast-emerging energy source globally. With the world energy focus lately being mainly on cleaner sources of energy, it estimated that by the year 2030 the consumption of natural gas would contribute to 26% of the energy consumption. Natural gas is commercially produced from oil fields and natural gas fields with gas obtained from oil wells called casing head gas or associated gas. Currently the proven two natural gas fields are South Pars gas fields in Iran and the Urengoy gas field in Russia. The Russian Federation proven reserve so far stands at 43 trillion cubic meters, whereas Quarter has at least 23 trillion cubic meters, 5% of the world's reserves so far, and is estimated to last 250 years at the current production levels. Most of the European community depends largely on the Russian Federation exported natural gas. Since the end of the Cold War in the 1990s, the Russian political stability has been good, thus making the onus of the supply dependent on the bilateral negotiations and agreements with regard to uninterrupted supply of the natural resource via the regional export pipeline. There are several local gas transmitting firms which will be able to provide dry and lean fuel gas at the potash plant battery limit, with the pressure reduction and custody metering facilities will be in the gas supplier's scope. Initial routing of the gas pipeline is also within the planning boundary of the supplier. Polyethylene glycol is a polymer compound with different applications from industrial to medicine applications. It is a family of long-chain polymer made up of ethylene glycol subunits and sometimes abbreviated as PEG. PEG is often used as a thickener in many products, as in detergents, where it is reacted with fatty acids, thereby showing the thickening and foam stabilizing properties. PEG is prepared by the polymerization of ethylene oxide and can be commercially availed over a wide range of molecular weights ranging from as little as 300 grams per ml to 10 gram per ml. The number after the name normally indicates the approximate molecular weight of the chain in a polymer. The higher the number, the longer the chain. Table 2 gives an idea on the current prices of the chemical polyethylene glycol and 4-week history of the price trend within the region. Even though there are a lot of brine sources scattered throughout the world, a few of them have been operated since the earliest days of the industry. The problem with mining potash is that the potash content in the ore is always weak, usually only about 1-2% KCl, IFDC, 1998. But new evolving technology and methods has led to profitable mining of high-grade potash from low-grade ore. The most effective method of mining high-grade potash from low-grade ore is the solution mining. There is a series of unit operations involved in this type of mining, but the most used unit operation in most mines that would lead to a marketable product are discussed in details below. Most of the potash deposits are found underground at depths of up to 2,000 kilometers. The potash mines use 3-pipe solution mining operation, IFDC, 1998. In this system, one pipe inject water near the top, then the second pipe would withdraw the brine from the bottom of the bed, and the third pipe is used to pad the upper surface, and these pipes were in one well, Garrett, 1996. After extracting the brine to the top, it is then that unit operations are carried out on the brine to produce the final product. 3.7.2 Evaporation. The first unit operation is the evaporation of the brine to crystallize dissolved halide. There are two different types of drying techniques or methods that can be used to evaporate the brine, being the solar evaporation and using rotary dryers. The solar evaporation step utilizes free energy from the sun to concentrate the brine and produce a plant feed, Garrett, 1996. In this process, the brine is dispersed on the impermeable soil, therefore an adequate area is needed. The sun rays would then evaporate most of the liquid part, hence leaving crystals behind. In some potash mines, for example Collium Chemicals, in Canada, triple effect evaporators are used to evaporate the liquid part of the brine, Garrett, 1996. Comparing this type of evaporation to solar evaporation, it is very fast and reliable. But it is more expensive than solar evaporation, which takes advantage of the free energy from the sun. The main requirement for solar ponds is that they should be an adequate area that is sufficiently flattened as an impermeable soil to support the evaporation, and also the land should be inexpensive and have a higher value use, such as agriculture, housing, etc. Since the brine has to be dispersed on top of the soil for evaporation, horizontal pollution can occur across the soil. 3.7.3 Drying. After evaporating the liquid part of the brine, heat is then applied to the crystals to dry them. A rotary dryer or spray dryer can be used to achieve this. In the rotary, the brine is fed to the upper side of the dryer. It would then be tumbled down due to the effect of rotary action and the effect of the slope. A hot gas, often air, passes up the dryer in the opposite direction, and as the solids are tumbled down through the gas stream, evaporation takes place, resulting in the solids drying. Roberts, 2009. For spray drying, the feed is pumped at the top and the atomizer would break it into small droplets, hence increasing the surface area to maximize drying as in figure below. 3.7.4 Separation techniques. Flotation. The dried brine contains potash and halide. Therefore, the next unit operation is to separate the potash from the halide. Many different methods can be applied to separate the potash, and one of them is flotation. It is a selective beneficiation process that utilizes the differences in surface property of various minerals. Wills, 2006. Also, it utilizes the principle that certain reagents will attach themselves to potash salts but not to halide, making it somewhat hydrophobic, not wet by water, and thus it will preferentially adhere to air bubbles. Garrett, 1996. The most important reagents used in flotation process are collectors. These are added to the potash mixture and time is allowed for adsorption during agitation in what is known as the conditioning period. Wills, 2006. After adding collectors, the mixture is bubble trough. This would lead to the potash particles being attached to the air bubbles, and then they would float on the surface of the aerated flotation cell. Then potash flows or is scalped off and the salt slurry passes out of the bottom of the unit. To maximize the flotation operation, the ore must be ground to a size small enough so that most of the potash is liberated from the halide, and the crystals of one are not attached or intertwined with others. An attempt is made to float as much potash as possible, while in the cleaner cells the purity of the floated product is the prime consideration. In this case, the waste from each stage is returned to the previous stage to be floated again. This operation is used in Germany. Figure 3.741 shows typical flotation cells used to float potash. Bet, 2005. Figure 3.7.41 Flotation cells. Electrostatic separation. One of the alternatives of the potash separation is the electrostatic separation. Also, similar to flotation, reagents are added to enhance the separation. Garrett, 1996. The mixture is then heated in a fluidized bed, and the relative humidity is adjusted to enhance charging of the particles. Then the ore is fed into the electrostatic separator to yield three fractions, that is, product, residue and middling. IFDC, 1998. Besides using collectors to induce charges, conditioning step can be used, which also induce the mineral to carry electrostatic charges of different magnitude, and if possible different polarities. In this step, the charges are induced through repeated physical contact between the different minerals. IFDC, 1998. Energy requirements, maintenance and operating costs are very low, and the process is extremely fast. Capital costs are modest, including some ceramic line areas for erosion control, and the separation process is very efficient. Sinchwald, 1983. Heavy media separation. A third method of separation that has been successful is the heavy media separation, which is based upon the difference in density of the minerals present. In potash mining, the process utilizes the difference in specific gravity of sylvite, KCl, and halide, NaCl. Halide has a higher specific density of 2.13 compared to the specific density of sylvite 1.9. So a liquid with an intermediate specific gravity halide would sink and sylvite would float. IFDC, 1998. The liquid of intermediate specific gravity can be obtained by the adding a heavy, finely divided, easily recovered solid. The cheapest and most convenient solids is magnetite, which is very heavy, insoluble and easily recovered with the aid of the magnetic force. Comparing these three methods of separation, flotation is the cheapest. It has reduced operating costs. However, it has disadvantages in that the major component of the ore is floated, which increase the reagent costs, and the larger particles of the insoluble remain with the product, decreasing its purity. The quickest operation is the electrostatic separation, which also has reasonable costs. Different mines employ or use these three different methods to separate the potash, with flotation as the most used. 3.7.7 Product screening. The last unit operation in the processing of potash is product screening. The screening of potash determines the purity of the final product, and to obtain a high purity product the operation should be quite intensive. Also, the size of the product should be considered when screening the floated potash. Different types of screens are used at different mines. In central Canada potash, they use 81.5x 6.1 double-deck Tyler T38 hammer screens to handle the hot flotation product from the dryers. This type of screens are very efficient and they almost recover 75% of the product feed. Garrett, 1996. At Cominco, the dried flotation product is screened in 81.5x 7.3 Rotex screens, which have a recovery of 85%. The Rotex screens are more efficient and have a larger capacity compared to the Hummer screens. But looking at capital cost, the Hummer screens are much cheaper even though their operating costs are relatively higher. In general, most mines use the Rotex screens because of their cheaper operating cost. 1464 words 3.8 Processing of potash ores and brines. Potassium chloride, potash, is one of those compounds which their processing is rather based mainly on physical means as opposed by chemical procedures. Even so, other forms of potash like potassium carbonate are derivatives of potassium chloride, that is, they are produced through reactions of potassium chloride itself with other reactants. Potassium magnesium sulfate, which is as well another form of potash, is produced by a similar procedure, that is, it has potassium chloride as a reactant during its formation. Garrett, 1995, pages 346. To process low-grade potash, potassium chloride, 4 basic beneficiation techniques are normally employed, namely flotation, heavy media separation, electrostatic separation, and thermal dissolution and crystallization. As for this discussion, only flotation and thermal dissolution and crystallization will be put into consideration. Unitintal Fertilizer Development in Treat Nations Industrial Development Organization, 1998. Chemical flotation. Flotation is basically a standard method formulated for separating potash from its accompanying halide. This is a selective beneficiation process which utilizes differences in surface properties of various minerals. By conditioning ores with feathers, selected minerals can be driven to become either hydrophobic, water repellent, or hydrophilic, water attracting. If a solution is then agitated with such agitators as the Ashton impeller and irradiated with a high-velocity air, normally done from the bottom of a flotation tank as in a figure 3.8 below, Strata 2006, which introduces bubbles, mineral particles which are hydrophobic will then preferentially attach themselves to the bubbles which coagulate, forming a froth as they rise to float on the surface due to lessened density, after which it then gets scraped off for further processing. The hydrophilic waste materials, gangue, which settles at the bottom of the flotation tank, is then removed. This type of flotation, which valuable minerals are removed in the froth, is termed as direct flotation, and it is the mostly common flotation technique applied in the potash industry. Unitintal Fertilizer Development in Treat Nations Industrial Development Organization, 1998, pp 140-145. In potash processing, the direct flotation process is carried out in a non-batch-based way, that is, it is carried out continuously. The most fundamental reagents in this process are known as collectors. For treatment of sylvanite ores, cationic collectors are added to the already closely sized, through comminution activities, and deslim slurry. These are primarily straight-chain aliphatic primary amines derived from natural fats and oils which are neutralized with acetic acid, CH3COOH, or hydrochloric acid, HCl. This addition is quite a critical activity since the functioning of collectors is highly dependent on pH, implying that the selective separation of minerals through hydrophobic and hydrophilic inductions of both waste and wanted minerals is under strict conditions determined by the pH status of the mixture. Therefore, its regulation is really vital for efficient mineral concentration. Unitintal Fertilizer Development in Treat Nations Industrial Development Organization, 1998, pages 144-146. The polar N group of reagents is selectively adsorbed on potash, resulting in its surface being hydrophobic, thus making it immiscible with water because the non-polar mineral surface covering molecules cannot interact with water, which is polar, as clarified by a universal law on solvents which states that like attracts like. Due to their hydrophilicity, sodium chloride salt, halide, particles and gangue materials sink in the pulp and are then removed through a vent at the bottom of the froth flotation cell. Garrett 1995, pages 340. In general, potash, NaCl plus KCl, plus gangue plus surfactant, collector, KCl, hydrophobic, plus, NaCl plus gangue, hydrophilic from Rao 2004. Since the collectors used are mostly organic compounds, the reaction is done at standard ambient temperature and pressure, temperature 250 Celsius and 1 atmosphere pressure. The reason behind being that high temperatures tend to bring about either denaturing or, more importantly, cracking of these compounds to a lower carbon chain organic compounds, which as a matter of fact have chemical properties which deviate from those recommended. Pressure is as well, and in doing so, less collection of minerals is obtained. The bubble rising rate becomes quite limited as bubbles experience a relatively larger resistance, and once again, if the pressure is lessened to subatmospheric pressures, the bubble rising rate becomes quicker, and in doing so, less time becomes available for mineral collection. Another disadvantage of tempering with pressure is that energy is consumed, and that increases the costs of the process. Frothers, which are some of the flotation process pre-applied reagents, are normally added to stabilize the flotation froth, as they act by inhibiting oversized bubble growth. This activity favors their coalescence upon rising up the flotation tank to the surface. Such reagents, frothers, are normally heteropolar organic compounds such as pine oil, which is one of the widely used frothers containing aromatic alcohols. A conventional frother, methylacebutocarbonyl, MIBC, is used as a modifier to inhibit formation of amines, as they tend to alter the pH of the reacting compound's concoction due to their affinity to hydrogen ions. Garrett 1995, pp 344. The applied concentrations of both frothers and collectors are normally as low as 0.05 gram per ton and 0.02 gram per ton respectively. Unitintal Fertilizer Development in Treat Nations Industrial Development Organization 1998, pp 147. As mentioned earlier on, the main objective of this froth flotation process is to separate sulfide, KCl, from halite through the use of cationic collectors, but more often than not, sulfate minerals such as kieserite are found to be present in the feed. Therefore, sulfated fatty acids are as well applied to render them hydrophobic, thus allowing them to be floated by rising bubbles. Collectors which are attached to the floating minerals, KCl, are then removed from them for reuse by simply washing away with plenty of water. This procedure is applied under the understanding that since the collectors have a hydrophilic end as well, they then attach themselves to the water molecules, thus allowing quite an almost perfect removal. As to be expected, the fine flotation treated potash is not up to grade, therefore, it is then hot or cold leached depending on its purity at this stage, after which it is then concentrated by evaporation before crystallization is undertaken. Garrett 1995. The process diagram below shows a plan through which the above described process is carried on. Fertilizer Manual, 1998. Thermal dissolution and crystallization. Besides flotation, thermal dissolution and crystallization process is used. This process is primarily based on the fact that potassium chloride is much more soluble in hot water than in cold one, whereas sodium chloride, halide, is on slightly more soluble at 1000 C than it is at 200 C. A saturated solution composed of both salts, that is chlorides of potassium and sodium. Sodium chloride proves to be less soluble at higher temperatures. To be more specific, when brine with both salts is heated from 200 C to 1000 C, a substantial amount of potassium chloride dissolves, but not sodium chloride. Unitintal Fertilizer Development in Treat Nations Industrial Development Organization, 1998, pages 140 to 145. After combination of sulfide or to at least a -3 mesh, it is then washed with cold. Saturated brine and clays are exterminated by dust liming, and the clarified solution is then heated before use in salvation of potash from its ore. Brine solution is then cooled under a no atmosphere, zero pressure system, and due to its highly sensitive to temperature solubility, potassium chloride crystallizes out and is thus separated, washed and slowly dried to allow better crystal growth. In other words, since the rate of change of solubility constant of potassium chloride is greater than that of sodium chlorides under temperature range 20 to 1000 Celsius, only a little of sodium chloride crystallizes compared to potash, and this allows quite a good yield. The residual brown is then recycled. To attain an even better purity, up to 99.9% by composition, potash is redissolved and recrystallized. The recrystallization procedure is normally done by introducing a potassium chloride grain unit into fertilizer development in United Nations Industrial Development Organization 1998, pages 143. Reaction equation: KCl plus NaCl plus H2O KClAq plus NaCl. A stage-wise process route of the above described procedure is as below. Fertilizer Manual, 1998. Problems engineers encounter under froth flotation process. The main problem encountered is that, due to an uneven flotation tank air introduction, there are places at which oversized bubbles are formed compared to some, and this is quite a problem since it inhibits proper and effective coagulation of bubbles, thus resulting in an unstable froth. To counter this, engineers have formulated modifier compounds such as MIBC, which controls bubble growth, RAW 2004. As for thermal dissolution and crystallization process, it is found that it is quite difficult to extract potash through the procedure alluded to earlier on to obtain an almost 100%, therefore, repetition of crystallization is done timely. Garrett 1995, pp 347. 1414 words 3.9 US and applications. In the section the uses of potash are discussed, give insights on its possible markets and its applications around the world. There are two main areas where potash is mainly used in the world, which are in industrial processes and as a crop fertilizer. The latter consumes about 95% of the world's production of potash. Drolet, 1976. 3.9.1 Fertilizer soils which have low potassium levels such as sandy soils need potash fertilizer to replace the potassium nutrient which is deficient in many soils. Drolet, 1976. Potassium is vital for many crop functions such as needed for healthy plant growth, helps in production and movement of starch and sugars, needed for good flower color and ripeness in fruits, needed for development of root systems and prevention of diseases. Drolet, 1976. 3.9.2 Industrial processes. Potash is the starting point of many chemical processes as it's an important raw material, especially potassium chloride, as it is very similar to salt, sodium chloride. Potash is many used in solution in the production of reagents like soda ash, caustic soda and chlorine, and these are the starting process of many chemicals which include the production of pulp and paper, glass, drugs, synthetic rubber, de-icing agents, water softeners, explosives, soaps, synthetic fabrics, explosives, glass and china production, soaps, biodiesel, liquid detergents and bleaches, insecticides and weed eradicators, and in chemical manufacturing such as sodium bicarbonate and hydrochloric acid. Andrews, 1991. The different way in which potash is mined and salt deposits determine chemical composition and chemical size. Solution mining produces very fine potash, which is important as it is used in the chemical industry but also consumed as a substitute of salt and seasoning and preserving foods, in curing meats and fish, in cattle and stock feed, in leather processing, in textile dyeing, and for dairy and other purposes. Andrews, 1991. Manufacturing of glass. Potash is used in the manufacturing of porous glass, which is used for making stable resistors and low-temperature thermometers, which are used in industry by cryogenic workers as its magnetic-induced errors are relatively smaller than other cryogenic thermometers. The disadvantage of this potash glass thermometer is that it tends to cover a small range of temperature change because of its drastic change in sensitivity with temperature. The applicable temperature range largely depends on the resistance of the thermometer at boiling point. The potash content may be increased in some cases to try and widen the gap of the temperature range, but this is only possible to a limited extent. Huang, 1989. Hydrochloric acid production. The potash grade of potassium chloride can be used for the production of hydrochloric acid using the electrodialysis process. To produce HCl from KCl, a 4-compartment cell is used with the 4 compartments separated by anion exchange membranes or cation exchange membranes. The 4 compartments are filled with different liquids which include potassium hydroxide, potassium chloride, hydrochloric acid and sulfuric acid. Anode are used. Markets. Canadian province of Saskatchewan is the world's largest exporter of potash as they have the world's largest deposits and most economic to mine. Its main markets are the United States, which accounts for over 68%, and the rest to offshore markets in Europe, Asia and South America. Drolet, 1976. The main competition of the world's supply of potash is between Canada, Russia and European producers. Drolet, 1976. The current provision of potash is from Canada as is very political stable and as it has the world's largest reserves and its good strategic location guarantees that it will continue to supply to consumer countries for a long time without major disruptions. Webb, T.C. and Smith, 2009. The demand for potash is steadily increasing year in year out, and this is due to countries such as China, India and Brazil, as it is used for widespread crop production in these countries due to population increase and changes in diet. Webb, T.C. and Smith, 2009. The predicted annual growth of potash is 4% annually, and this is equivalent to 2 megatons per year increase. This is good for potash suppliers as there has been a lot of oversupply of potash in recent years and will help ease competition from suppliers. The population of the world is expected to increase by over 40% by the year 2050, and this is going to push the demand of potash-based fertilizers to the maximum. Webb, T.C. and Smith, 2009. Several factors are influencing long-time demand and supply trends for potash. Canada continues to be the world leader in producing and exporting this strategic resource. Webb, T.C. and Smith, 2009. Apart from extensive potash resources and the associated development in Western Canada, New Brunswick is the only other region in the Canada where potash is mined and processed. New Brunswick is also the only potash producer on the east coast of North America. New Brunswick's potash exploration and subsequent development spans nearly 4 decades. Webb, T.C. and Smith, 2009. Potash resources have served the province well, supporting world-class mining and processing facilities. Not only is the potash industry a sign if I can contribute to the value of the province's mineral production, it also acts as an important contributor to New Brunswick's economy. Webb, T.C. and Smith, 2009. The potash industry is a source of considerable revenue and benefit, via taxation and royalties, the purchase of domestic goods and services, and employment for up to 400 persons. Webb, T.C. and Smith, 2009. 919 3.10 Safety, Health and Environment. She is an integral part of the mining business. It is a company's responsibility to monitor the safety, both of its workers and the environment. Mining groups need this for a good reputation in their local societies and with prospective business partners. Safety and health must be monitored to achieve high environmental standards. Tomlin, 2009. Non-compliance to environmental objectives in mining can result in social, economical and sometimes political instability. This section of the project is aimed at discussing hazards posed by the mining of potash, risk management measures including short and long-term environmental impacts. Further discussions on waste management and monitoring techniques are also included. 3.10.1 Employee Empowerment on Safety for Risk Management. Employees have to be sensitized with health and safety issues, particularly those involved in the processing and mining activities. This will improve the staff's approach to handling accidents and incidents in the workplace. Different companies have their best chosen risk reduction techniques. Potash Corp., 2010. Explains that they have short courses offered for supervisors, regular briefings and workshops for other workers. Potash Corp., 2010, focuses greatly on the concern for human life and accident prevention. They also base on motivation of employees on the personal safety ethics. 3.10.2 Hazards posed by equipment and people in the mine. Several hazards posed by process equipment, material being processed and the mine surroundings come at different stages of mining. During the mine development stage, which involves exploration, planning, construction and assessment, the main environmental impacts to consider are noise pollution, air emissions and water contamination. Garrett, 1996. There is usually problems of creep and severe stress during the extraction of brine from deeper layers of mining site. The chosen process route in this report, solution mining flotation, could pose the mine with a number of dangers. These include potential flooding from burst underground pipes, rock burst from trapped high temperatures, combustible gas and an unstable roof. Garrett, 1996. It is therefore a responsibility to the safety officers to ensure that conditions are well met to minimize accidents. High pressure, gas-saturated hot brine deposits pocket themselves between rock gaps. They dissolve some salts as pressure builds up and as a result, the rocks burst. Geological monitoring of the mining phase has to be established to avoid serious rock burst problems. With longwall mining, methane occurs with shales. Accumulation of this toxic and flammable gas may cause explosions that could injure workers or even lead to death. Slow decomposition of organic content from algae in the deposit could give off hydrogen sulfide and carbon dioxide gases that accumulate, resulting in rock bursting and gas explosions. Rock bursts occur due to high-pressure water aquifers. The sylvanite ore has pockets of high-pressure gas. These are primarily the factors that have led to the extensive use of pillar mining. Garrett, 1996. The ore usually has a high shale content. This poses a risk to the on-site workers as there could be dust particles that could affect their health. In addition to the latter mentioned impacts at the extraction stage, removal of overburden will cause a destruction to land surface, topsoil degradation and vegetation and wildlife destruction. These also occur during ore handling, transportation of raw materials, storage and reclamation. Potash Corp., 2010. Potash mining is also done in underground shafts. A tunnel is carved off and men go in with big trucks and machinery to dig off the potash in powder form. They are all at risk of dust exposure and roof falling. The picture below shows how the tunnels are made, which is a safe method as compared to surface mining, for reasons to be discussed in Section 3.10.3.3.10.3 Environmental Impacts of Extraction Process and Potential Risks in Case of Failure in Russia. Dmbrov Mine in the Kalush region is the world's only open-pit potash mine. Gareth. Open-pit mining has many effects on mine parameters. For these reasons, many potash mine operations have been done underground. Emissions such as aerosol deposits from surface mine blasts cause climate change and variability. Some of these have a long atmospheric lifetime. They circulate around the globe and mix with the stratosphere. The ore is covered by clay, gravel and argillaceous alumina. In surface mining, there is usually a lot of sources of dust, including surface pickup. Topsoil is drilled and gets loose. Dust particles get picked up by high wind velocities. Haulage and raw material transfer. Traffic in and out of mining sites driving at various speeds also loosen the topsoil on site. They cause air turbulence, which results in displacement of dust particles in the air. Vegetation on mine parameters is usually dust-coated and dull-colored. Birch, 2009. Dust control is usually accounted for during the planning stage of a mine. Many have employed several control measures to reduce the effects of dust in the atmosphere. An example is conveyor sprays, often used to keep materials wet and dust-free during transportation. Birch, 2009. Monitoring emissions is important to ensure compliance with the planning conditions, help in perfecting designs for any future projects. Since potash seams are usually surrounded by clay deposits, the clay contains some chemicals such as alumina, which in large doses can become chronic in humans and animals exposed to it. In underground potash mining, which is the main focus in this project, ventilation is important. There is a need for air-controlled doors in some entries and good airflow in all working areas. Underground airflow is needed. Workers to have uncontaminated, fresh air to breathe. Auxiliary fans are often used to divert air across each mining machine to help cool them down and blow off toxic gases such as carbon dioxide, carbon monoxide, methane and hydrogen sulfide, which result from potash mining. Garrett, 1996. Extensive cooling is important as rock temperatures in potash mines reach highs of about 38 degrees, therefore is not safe for workers on site. Safety precautions should be taken so as to reduce the rate at which pollutants accumulate in the atmosphere. Figure 3.10.2 below indicates the greenhouse emissions for a typical potash mine. With proper precautions taken, these figures could be reduced. Most of these show to be coming from direct emission dust particles that escape during mining and transporting of potash through operations. These are primarily from the combustion of natural gas. Indirect emissions are mainly based on the use of electricity, NRCan, 2009, 3.10.4 tailings and waste management. Historically, salt tailings and slimes were stacked and impounded on surfaces. For mines near rivers, they used them as a tailings dumping site. Insoluble slimes and salt tailings become a problem in potash mining as they endanger aquatic life in dosages too high than needed. Saskatchewan, 2010. Potash mine in Canada has been susceptible to flooding problems. Water flooding is one of the most severe dangers of many potash mines, which the Canadian mine experienced while trying to reduce leakage in their shafts. This occurs when cracks connected to an aquifer, the passageway resulting from dissolved salts. Consequently, uncontrolled water enters the mine. Overflooded mine shafts are usually abandoned. This results in potash from these sites seeping out to contaminate soil and underground soils in the surroundings of the mine site. When the underground water reservoirs accumulate high potash content, it affects the purity of water in nearby townships because potash is completely soluble in water. It is ethical to pay attention to risk in a relatively same way as benefit. Some techniques developed to reduce water flooding includes establishing of aquifers by surface drill holes, employing of large pillars in more hazardous areas. Preventing of crack initiation and propagation is achieved through grouting of small leaks by injecting cement or polyester resins into the leaking area. Garrett, 1996. Rock bursts and methane explosions are another hazard that potash mines are vulnerable to. Measures to monitor this could include increasing ventilation, replacing carbide lights with electric ones, and the use of explosive-proof electric equipment. During the planning stage of a mine design, geological testing is usually performed to determine panel location, design and sequence of a mine. Preliminary surface drilling to observe potash seam thickness, slope and grade to decide on mining progresses. For the safety of the workers, and it is economical so to avoid disasters, as mines usually have areas that should be avoided. In a nutshell, the health of the workers, animals and people in the mine parameters are threatened by emissions. Dust particles cause a high prevalence of cough, dyspnea and chronic bronchitis. Solid and liquid forms of sodium chloride are some forms of waste from potash mining, clays with minor amounts of minerals such as gypsum. All these are usually disposed of as slurry into waste disposal basins, and brine volume reduction is done by evaporation. These tailings dams or slurry basins are monitored by sequential sampling. Tests and analysis are performed to check the quality of the formation water. Saskatchewan, 2010. 1498-3.11 Process economics. When constructing, running and maintaining a plant for potash process, the first task would be to estimate or assess the economic feasibility of solution mining. Therefore, the best way would be to estimate fixed capital costs and potash production costs by solution mining and refining for a variety of conditions that might be encountered. A number of hypothetical cases must be established and assessed to provide general cost information. Standard engineering methods must be used to calculate the fixed capital cost and the total production costs of potash manufactured by each process. The steps involve are development of flowsheets, calculation of material balances, calculation of equipment size, calculation of utility requirements and the size of auxiliary services, calculation of fixed capital costs, calculation of operating costs of utilities, and calculation of product costs. Garrett, 1996. Profitability must be determined by calculating payout periods and rates of return upon investment. On the basis of the established flowsheet, material balance calculations should be carried out for ore grades of K2O and for production rates of tons of product per year. The sizes of process equipment should be calculated and their performance requirement must be determined. The data should be sent to equipment suppliers and price quotations are obtained for major processing equipment, drilling and completion of brine wells, steam and power generating equipment. Economic data at each phase of the planning cycle of potash. First review of a new project. A broad brush mine plan uses rules of thumb based on industry experience to ascertain the likely project economics. The fundamental economics of most mines are set in place by no more than 4 or 5 factors, which usually are depth, waste, or ratio, or characteristics, type, grade, plant yield, the selling price, and the distance to the market. It should be identify any particular production, market, or other constraints or risks that could potentially impact the project revenue. Strategic planning and development strategy. This is the key phase of the project. It is a phase when critical decisions are being made concerning development strategy and alternatives with substantial differences in economics are eliminated. Following this phase, the fundamental economics of the mining operation are largely fixed. Changes in strategic direction have major influences on costs, risks, and capacity to accommodate change. Once a strategy has been adopted, subsequent work, the phases following this step, results in more evolutionary influences on costs and risks. Evolutionary change may not result in large changes in costs of production, but it may still result in significant change in profitability. Further, the cumulative effect of extensive evolutionary change over time may permit change in broad strategy, with substantial impact on costs of production. The scope for such cumulative evolutionary change is also a part of the strategic planning phase evaluation. Detailed long-term plan or feasibility study. This phase involves at least two different types of economic evaluation. Within each cost center or definable activity, the optimum mining scheme should be determined. For example, for waste removal, the proportions of waste moved by trucks, cast blasting, or contractor O. This type of economic evaluation is undertaken by discounted average cost calculation or similar techniques, restricting inputs to those factors likely to influence the result. For whole mine evaluation, the complete operating and capital cost for the mine should be developed and tabulated, leading to the whole mine cash flow analysis. Equipment selection. Optimization of equipment sizing and trade-offs between different machines must be undertaken on a relative cost basis, usually using some form of discounted cash flow analysis. Frequently, equipment selection also involves the comparison of mining alternatives, whereby some equipment purchases are delayed, either to save initial capital or because there is insufficient working room available in the early stages of mine life. These evaluations involve alternative mine schedule. Mine development phase. In the mine development phase, most of the decisions influencing the economics are complete. This phase involves setting up the systems to compare actual costs and quickly highlight anomalies. The process also involves auditing of accounting procedures to ensure that precedents established for tracking of costs do not result in day-one deviations that are then not discovered in subsequent accounting within the mine year planning. This is normally undertaken by using costs already established from prior experience. Monthly planning. This is normally undertaken by using costs already established from prior experience. Weekly and daily planning. Guidelines prepared for more exhaustive general studies should be summarized to allow personnel to make day-to-day decisions based on economic criteria. Runge, 1998. Strategic issues in potash mine development. One key strategic factor affecting revenue. The key strategic factor affecting revenue or selling price of product, including premiums or discounts for quality characteristics, quantity and quality of product produced, quantity of product able to be sold, including transport constraints and factors likely to disrupt mine output, and startup scheduling problems in the mine or mill delaying initial deliveries. Two key strategic factors affecting cost. The key strategic factors affecting cost are surface mines, waste removal costs, rehabilitation costs, underground potash mines, development to establish primary workings, roof support, ventilation costs, underground hard rock mines, development and access costs, drilling and blasting cost, backfilling costs and ground support, inquiries, fragmentation, environmental constraints. Runge, 1998. A very important factor for an individual mine's long-term production is that potash, as any mineral, is a depletable resource. As time goes by, the mineral ore is removed, and unless other seams or nearby deposits are available, the mine runs out of ore. Usually this happens quite gradually as more difficult, expensive, or lower-grade reserves are mined, and the production slowly diminishes. This has now occurred with many of the older mines or deposits, where for a large formation some of the mines began to close, others consolidated, and the remaining slowed their production. RV, LC. 1924. Comparison of mining equipment options. Mining operation continually change. Existing equipment becomes less suitable to the task. New equipment is continually developed to move mining quantities more cheaply. in an ongoing mining operation, or in the detailed planning phase of a new mining development. The most common task requiring economically analysis is the exercise to compare potential alternatives. Runge, 1998. Comparison of cost solution mining versus conventional mining. In order to have an appreciation of the competitive position of solution mining in regard to conventional mining and provide cost data for comparison, capital and product cost estimates should be made for conventional mining and refining under similar conditions but with potash at a depth of 3,500 feet. In view of the characteristics of potash ores, two processes should be considered for conventional mining and recovery. Process 1 should be based on flotation. It should be assumed, for example, that 4% of the ore would form slimes which would be discarded. Process 2. The potash should be recovered by flotation and supplementary crystallization. The ore should be assumed to produce, for example, 9% slimes which should be treated for recovery of potash. Fixed capital requirement and product costs for conventional mining and refining should be estimated following the procedure mentioned earlier for solution mining and refining. Short-term and long-term costs. Long-term cost planning involves large purchases that will return a financial benefit over time, usually greater than 1 year. A long-term investment may be purchasing equipment to produce a new product or to make an existing process more efficient. In either case, the expected future return is greater than the initial investment. Short-term cost planning involves purchases for things like raw materials and extending credit to customers. This type of planning deals with issues over a time period less than 1 year. Snow, 1997. Overall project evaluation. The evaluation of an overall project should be usually undertaken by using discounted cash flow techniques. A technical study initially yields tabulations of the required equipment, personnel, and supplies necessary during each year of a pre-production and production to produce a certain amount of mine output. The costs of purchasing and operating the equipment should be combined with personnel and others costs to determine the overall cost structure of the mine. The expected revenue from the sale of the mine output should also be estimated. A cash flow tabulation sets out all of these cash inflows and outflows year by year, including tax payments, to determine the annual cash flows for the project. Torres, 1998. When a potash ore has no market price that can be used or adjusted, the economic price has to be estimated some other way. It is mostly environmental aspects and impact, positive or negative, that have to be valued without reference to market price, because no markets exist for the goods themselves. Collier and Glagola, 1998. 3.12 Conclusion. The research shows that the extraction of high-grade potash from low-grade ore is a process which uses a lot of physical methods compared to chemical methods. Even though there are chemical substances used like polyethylene glycol and hydrochloric acid, these are used to speed up the process during purification and drying. Most of the raw materials used in the operation are found natural and are cheap, like water, which is the most used substances. It was found that there are a series of unit operations involved in potash mining. Extraction being the first one and involves the getting the potash from its ore. Since the ore used had a low-grade potash, it was concluded that the best method of extraction was solution mining. After extraction, the raw potash is dried and then it undergoes separation techniques. Most used separation technique in the mines was found of flotation because of its simple science and it is relatively cheap. But most important is that flotation recovers more than 98% of the pure product. The final unit operation was product screening, which increases the purification of the product. In economic process of potash, the most important thing is minimizing operating cost. Low operating costs are particularly important for export-oriented mines, since the price of mineral commodities sold on the export market is usually more volatile than that of similar commodities supplied to domestic markets. Indeed, some domestic contacts used cost-plus pricing, in which case the incentive was to increase operating costs. One of the most important tasks when constructing or running a plant for potash was to assess the economic feasibility of solution mining. Therefore, the best way was to estimate fixed capital costs, potash production costs, by solution mining and refining for a variety of conditions that might be encountered. The total fixed capital investment estimated for the refinery was always based on the quoted price of process equipment. Other cost items were estimated in the form of percentages of the cost of process equipment. In potash plant operations, cost depended upon the size of the plant and upon the hours per diem during which operated. Safety is one thing that should be practiced in the extraction and production of potash, since there are a lot of risks and also pollutants are released during the operation. Pollutants that are emitted from the potash mines include aerosol particles which have an effect on climate change. Also, there are poisonous gases released during extraction which are dangerous to human health and the environment. Fortunately, it was found that most potash mines have equipments that are designed to reduce pollution or convert poisonous gases to environment-friendly gases. Besides pollution, there are risks involved in the pipes that carry hot liquids. Gases can bust, sometimes resulting in flooding. Also, the equipment used for extraction is very heavy, hence it exerts too much stress on the ground that can cause some tunnels underground to collapse. The best method to minimize these risks was found to be prevention, and mining companies should have safety officers to ensure that good conditions are well met. 509. 3.13 Acknowledgement. The quality of this report was greatly boosted by the kind assistance of Amanda Lee Yankton, the project supervisor. Our deepest gratitude goes to her for the patience and guidance throughout the research project. We would also like to acknowledge our module leader A. Borisova for assigning this task. It has helped all of us learn to set aside our different personalities and backgrounds to be able to get some work done. This is an integral part of our degree, as it paves way for good working relationships once we join the professional world. Many thanks to all the group members for sacrificing their time through the Easter break and canceling their holiday plans to put effort in the project compilation. We are grateful to all sources of our information and those who contributed ideas, directly and indirectly. This report would not have been a success without their gracious contribution to the group project. Anybody else who has given us support to enable us to come up with this write-up, your effort is sincerely appreciated. 177 words. Reference 1, Bateman Engineering Technology. 2005 Flotation Cells, online accessed on March 29, 2010. Available from http://www.bateman.co.za/ BetFlotationCells.htm2, Birch, J.W., 2009. Dust PME 1200 Lecture Notes. Leeds University, SPME. 3. Collier, CANCR, Glicola 1998. Engineering Economic and Cost Analysis. 3rd ed. California. Edison Wesleyman, Incorporated 4, Harvey, L.C. 1924. Pulverized Fuel, Colloidal Fuel, Fuel Economy, and Smokeless Combustion. London. McDonald and Evans 5, International Fertilizer Development Center, 1998. Fertilizer Manual. The Netherlands, Kluwer Academic 6, Garrett D.E. Potash, Deposits, Processing, Properties and Uses. London, Chapman and Hall, 1996-7, Potash Corp 2010. Safety. Online. Accessed February 24, 2010. Available from http://www.potashcorp.com/ about/ sustainability/ safety/ 8. Roberts, G.K. 2009. Batch Processing for Fine Chemicals Manufacture. Lecture notes distributed in PME 1080. Process and Production Engineering. University of Leeds. October 9, Runge, IC. 1998. Mining Economics and Strategy. Littleton, Colorado, USA. Society for Mining, Metallurgy and Exploration, Incorporated 10, Saskatchewan, 2010. Saskatchewan Eco Network Issues. Potash. Online. Accessed February 21, 2010. Available from http://www.econet.sk.ca/ issues/ mining/ potash.html page top 11, SNOW, M 1997. Cost-benefit analysis for engineers and planners. London. Thomas Telford 12, Tomlin, Prof. 2009. PME 1200 Lecture Notes. Leeds University, SPME 13, Torres, T, F 1998. Evaluating Mineral Projects, Applications and Misconceptions. Littleton, Colorado, USA. Society for Mining, Metallurgy and Exploration, Incorporated 14, Wills, AB 2006. Minerals Processing Technology, 7th ed. London, Elsevier Ltd. 15, Mineral Resources of Saskatchewan, 2009. Online. Accessed February 23, 2010. Available from www.saskschools.com/Gregory Sask HTML16, Natural Resources Canada, 2009 Energy Benchmarking, Canada Potash Production Facilities. Online. Accessed February 21, 2010. Available from http://oe.nrcan.gc.ca/ publications/ infosource/ pub/ CIPIC/ potash-production/ images/ fig3.gif. Thank you for taking your time to listen to me. I hope you enjoyed learning about high-grade potash from low-grade ore as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at All A+ Essays for as little as $10. The link is in the description. See you next time.